Thank you. So as you know, we had a slight change of schedule, and so Jordan Reed was so nice to say he could move up. So Jordan Reed from the United States Geological Survey will be talking to us about perspectives from the US Geological Survey about advancing water prediction with knowledge-guided machine learning partnerships. Jordan, take it away.
Oh, great. Thank you, Amy. Apologize if you're tuning in for Elizabeth Barnes or Professor Barnes' talk. I really look forward to what she presents, and she just gave an excellent talk, and we're switching time slots here, so I'm presenting a bit earlier, but hope you were able to tune in to the talk right before this, as Libby once again gave an excellent talk. So I'm here to talk today about advancing water prediction within the US Geological Survey, specifically through a number of different partnerships and collaborations. And I'm giving this talk from the perspective of the USGS Water Mission Area. I run a data science branch and oversee a collection of teams, many of which are working very directly in this field of advancing knowledge guide machine learning. So one thing that might get you a bit hungry, maybe a bit too hungry before we step into the afternoon break, is this slide. So I apologize for that in advance. It's already making me think beyond my breakfast into what I might have for an afternoon snack. But this image really connects to the core message that I'd like to share today. So if you look to the right side of this slide, tomato soup is creamy and tangy, and grilled cheese on the left is rich and salty, but alone, the two of these are underwhelming. Together, however, they're a complementary team that offers a really rich flavor profile, which didn't exist when the two of them were on their own. Tomato soup and grilled cheese go hand in hand, and we know that they work best together. But some pairings, like the relationship between a federal science agency and academic partners, might not be that obvious. So as walking you through this presentation today, I'm going to try to make those connections clear. So how can collaboration totally shift the possible outcomes of a situation? And how does tomato soup and grilled cheese relate to water science and machine learning? There are a few ways that I'm going to address this question today, and we'll return to the grilled cheese metaphor at the end of the slide. So let's talk first about collaboration and how it relates to our topic of machine learning more than grilled cheese does. We can take two things that as alone they are useful, but in isolation they may fall short of what our ultimate objectives are, specifically applying something to complicated science questions. So in past work, we've been able to harness the power of collaboration on numerous levels, and that collaboration shows up in various places, and we'll be talking about a few of them today. So this is an image of the Delaware River Basin. This is the northeast of the United States. You may recognize a few of the neighboring states within the basin. But in order to make effective and informed decisions with natural resources, such as those within the Delaware River Basin, we need awareness of possible future events and the understanding of what likely happened in the past, such as the outcomes of prioritizing water for drinking and the impacts that might have on aquatic habitat, such as the habitat for these cold water trout that are pictured below. But our current modeling methods often fall short of providing adequate information to address the problem. So we use a combined method to more accurately answer pressing questions like, do we release water or not from these reservoirs? So New York City reservoirs provide drinking water for approximately 15 million people, but these are limited resources, and they also are used to maintain downstream habitat in the Delaware River Basin that supports a world-renowned fishery. In these reservoirs, there's a finite amount of cold water that can be released, but the downstream water temperatures must stay below a certain threshold to protect threatened and endangered species, including the cold water trout featured on that prior slide. So this collaboration, both a collaboration in modeling and across institutions, has an objective to forecast future downstream water temperatures with consideration to these water releases, thus enabling us to more accurately and precisely understand the implications of whether or not to release water. But hang on, what's our modeling method and who are we? So knowledge-based modeling, often referred to as process-based or physics-based model, defines equations that capture our understanding of how the world works. And we use these equations to make predictions. Machine learning, on the other hand, discovers its own equations based on data. In isolation, these methods can be extremely powerful, but are unable to meet our current prediction needs. So enter knowledge-guided machine learning. To improve water predictions, we've embarked on a collaboration between the best of both modeling approaches, resulting in this knowledge-guided machine learning. But who are we in these collaborations? I represent, or I'm speaking on behalf of one of the science agencies here, the US Geological Survey. USGS collects massive amounts of water monitoring data and provides reliable science to the nation, but alone we lack disciplinary coverage, for example, computer scientists and many other technologists. We also have limited capacity for embarking on high-risk exploration, and by extension, we really have a lower capability for rapid innovation. So collaborations with our academic partners are key to disruptive advances in water prediction. The US Geological Survey is the primary monitoring and science agency for the nation's interior. That means our scope includes all of the environments of the United States, even nearshore coastal ecosystems, all the way to volcanoes. And a wide breadth of science is covered by 4 topical mission areas: ecosystems, energy and minerals, natural hazards, water resources, and a single cross-cut mission area called Core Science System, which is designed to integrate across these other topical areas and provide scientific support and infrastructure such as high performance computing. But today we're talking about water prediction. So let's focus on how these early efforts to quantify water in the Western US and an evolving set of water priorities have resulted in a huge resource of Earth observations and science outcomes that are primed for collaborative engagement. So this water resources mission area is focused on monitoring and understanding all aspects of water availability and water quality, including different needs and uses of water for ecosystems and industry. The most visible part of the USGS water effort is the National Stream Gauging Network, which has been collecting continuous river flow measurements since 1889. And yet you heard me right, 1889, so well over 100 years. Through that time, over 50,000 gauging stations have come and gone, and over 8,000 remain that are used for all kinds of different research, and also used by the National Weather Service to forecast floods. Because of this real strength in the data program, there's been a historical partitioning with all kinds of different elements of USGS, going all the way from funding to different staff roles and specialization, including the strategy for how these different activities have been carried out. So if you can imagine the science of how we make measurements of the natural environment, and specifically in water, has evolved. There is lots of innovation to be had with designing sensors and also how we store and deliver data. These differences appear in numerous scales. So USGS has a number of different regional offices, typically at the scale of about a state or a couple states. And this difference in data, or this specific role in data, also extends all the way up to our headquarters program, of which I'm a part of, which covers the nation and its water priorities. We have 2 different distinct funding sources at the USGS. One that's primarily aligned with data, and the second that's primarily aligned with advancing studies. So just as USGS Water has developed strength in making and delivering observations of the water system, we've also been able to accumulate a great amount of knowledge, which we refer to as the studies program, which is really how the water system works. A lot of that is translated into numerical models, such as mod flow, which is shown here in the left-hand side. And this division between studies and data extends all the way from, like I said before, the funding of how these two different bodies of work are funded, and also how they're designed to move forward. We have programs for water prediction, drought, and 5 others that are aligned with this studies source of funding. And then 7 more programs aligned with data, including one that's called the Next Generation Water Observing System, which we call NGWAS for short. This set of different programs is funded by the approximately $250 million congressional appropriations that go to the water mission area from Congress. So the prior slide focused on this partitioning between data and studies. Some USGS specialists focus on designing model equations as part of that studies body of work. So we, with this accumulation of all of this data from the USGS, naturally looked towards new advances in machine learning that could help us discover from data. USGS does not have traditional expertise in the most advanced forms of data-driven modeling. But of course, we're seeing all that is going on in leveraging these massive amounts of new data streams, and how data-driven models began to quite easily beat the accuracy of our designed model equations in terms of accuracy. This New Yorker example from an article showed that a deep learning model was able to be trained on the corpus of writing from the New Yorker and able to emulate the writing style of that magazine. So of course, if you're thinking about modeling the water system and you see a model that can approximate a particular writing style of a magazine, by extension, you imagine that a similar modeling approach might be able to, for example, provide a more accurate estimate of the timing of snowmelt than our current modeling equations that are designed. So that, of course, led us into these strong collaborations that I mentioned earlier. We knew that there was a great deal of promise in leveraging advances in deep learning, but at the time, of course, lacked the expertise to embark on those. So combining our efforts, our understanding of these knowledge-based or designed models with the vast data resources of the USGS, we connected with our academic partners. And of course, instead of looking at modeling as a trade-off between design and discovery, looked at it as a collaboration between design and discovery. So instead of or, it becomes and. Our early work looked to draw contrast between these different models. So a model that is designed based on an understanding of the way a lake or reservoir behaves. So it's conservation of energy. So the incoming and outgoing energy fluxes as a lake interacts with the environment are captured in equations, and that model can be driven with inputs of weather. One advantage of this type of model is that when there are no data or very little data, it can still provide usable predictions. But of course, as we add more and more data, this model isn't as available or isn't as able to leverage additional information to improve the accuracy of its prediction. And then of course, the contrast is a purely data-driven model, or in this case, a neural net is able to beat a designed model or a process-based model when given enough data. But of course, if we remove more and more data from this model, which is typically a data-hungry model, it will fall apart and definitely not be able to perform at all when we confront it with no data that would be available for training. So of course, the collaboration between design and discovery becomes knowledge-guided machine learning, which is able to take advantage of the best of both worlds. So models that are both designed and are allowed to discover and modify responses to the inputs. So coming back to this modeling objective, and this is one of many different modeling questions that may come up, but of course is the feature use case of this talk, whether or not we want to release water in this Delaware River Basin from reservoirs. And this specifically is a decision for reservoir operators. The fruits of this collaboration and really the foundational building blocks to make this question something that can be answered have come in the form of a number of different modeling architectures and advances as captured in these papers throughout the last 4 years. So these initial papers that I'm highlighting here provided new knowledge-guided machine learning methods approaches to make stream and lake water quality predictions more accurately. And these were critical advances because they were able to make predictions that were accurate enough to be usable for decision makers. And those decision makers were able to communicate their needs for accuracy of model predictions to us in the form of our forecasting problem with water releases, having a root mean squared error below a certain threshold for a decision, and also in other collaborations with fisheries researchers and managers to have accuracy root mean squared error below 1 degree C in order to make informed decisions about the future and past of a inland fishery. Next, these models were tested or modified in a way that we were able to make predictions out of bounds. And these two papers highlight two very different applications of out of bounds predictions. So the 2019 paper in Water Resources Research showed us that by exposing these knowledge-guided machine learning models to synthetic predictions from a knowledge-based model, we were able to make predictions in an extreme period that was held out from the training data. So in that case, it was withholding summer training data from the model and asking a model to predict summer water temperature conditions. And as you can imagine, those are quite different than the adjacent seasons of spring and fall, and definitely quite a bit different than wintertime temperatures. And then the paper by Jared Willard that just came out this year and also in Water Resources Research used meta-transfer learning to decide which trained model could be applied to an unmonitored system to maximize the accuracy of that model on that otherwise unobserved system. So really great advances that both provide extension to where these models can be used and also provide additional confidence in their use. And also in working with decision makers that are using predictions, it's critical to have some estimate of uncertainty in those model predictions. In the past, that has been lacking from many of our use cases for modeling, including process-based or knowledge-based models, and definitely also in data-driven models. But that's a critical piece of information that is necessary for the use of these predictions. And so in Arkadaw's 2020 paper, there was a dropout uncertainty quantification method used to estimate uncertainty in a kgml approach. And then also in Jake Zwart's forecasting paper, uncertainty was also quantified as part of producing forecasts. And so these different pieces led us to the ability to combine knowledge-guided machine learning with data assimilation to produce near-term forecasts of stream water temperature that also includes the impact of that decision, whether or not to release that cold water that is contained within a reservoir in order to cool downstream habitats. So coming back to that original question that we have. And I also point you to Sam Oliver's presentation in the aquatic session that is coming up later this week. So in summary, these knowledge-guided machine learning partnerships between USGS and our academic partners are really creating new modeling strategies for solving real-world problems that are integrating their way into USGS scientific strategies. So for example, knowledge-guided machine learning, or as it's referred to in a lot of these strategic plans, process-guided deep learning, is already a priority in several of these new USGS water programs. It's part of current projects and part of the plans of future projects, which will tap into this new modeling approach. Also, in these communities of practice, we're exchanging data, code. We're working together to make these models more reproducible, more transparent, and understandable as we collaborate openly with publications and also with data releases and code releases that accompany those papers. And lastly, as a major boost for the US Geological Survey, the outcome of having KGML science be a big part of training the next generation of water leaders. So some examples of that, Allison Appling, who is a co-lead of the aquatic session later this week, is now running the strategy for the application of machine learning in the USGS water mission area, and is overseeing the launch of 5 new projects next year that will use knowledge-guided machine learning as part of their modeling architectures. Also, Sam Oliver and Jake Zwart were able to jump on this opportunity to make forecasts for water temperatures in the Delaware River Basin and create successful models and data releases for that. And lastly, we've been working with a graduate student, actually with several different graduate students, but one I'd highlight is Jared Willard out of the Kumar Lab, who's doing a USGS internship on KGML work and will be soon in the fall moving to work with DOE as part of a fellowship. So Department of Energy is another federal science agency, which is also continues to be very interested in leveraging knowledge-guided machine learning for their purposes for advancing their models. So returning back to our grilled cheese and tomato soup, as we're now getting ever closer to the lunch break, I wanted to remind you of this collaborative thread that's been woven throughout this talk, which is these two things, which are pretty great, but combining them thoughtfully through collaboration can make them even better. And just a few things that we touched on. So the posture of a federal science agency being a natural complement to the academic opportunities for rapid innovation and high-risk testing. Also, the pairing between a long-running data program, such as what the USGS has, and also being able to use that to train and build models. And lastly, of course, is the basis for this workshop. So knowledge-guided machine learning. So the idea that we take knowledge-based models and can combine them with machine learning approaches to create a new approach that is even better with this collaboration in mind. So thank you.
Thank you so much, John. So here's a question for you, Insider. John, if someone at a university is interested in working with USGS or other federal agencies, how do you suggest getting that collaboration started?
Yeah, that's a great question. So USGS has a couple of different funding vehicles that make that collaboration with funding possible. We have a competitive set of grants that come out of the Water Resources Research Act, which is one of the congressional appropriations that I didn't refer to, but Those competitive grants come out once a year, and the present pot for funding is at $11 million. And each one of those grants needs to have at least one USGS partner as part of the proposal. So that's one way. A second way is to engage directly in collaborations by reaching out to connect with anyone you might know from USGS, and that could be emailing me, it could be emailing Allison or Sam or Janet Barclay, who's also presenting later in the week, or anybody that might overlap with your particular area of interest, and talking to them about collaboration, depending on whether or not that collaboration would require funding on your part or not. Kind of sets it up for a different level of engagement. We have the ability to fund graduate students and also academic PIs through other agreements with universities, and that's actually quite a bit streamlined for land grant universities as well, but not restricted to land grants. So I would say definitely reach out to us.
Great. The next question that came in, are KGML approaches suitable for multi-objective water resources problems?
Sorry, could you repeat that one?
Sure. Are KGML approaches suitable for multi-objective water resources problems?
Oh, great question. Apologies, coughing a little bit. So one of the papers that I glossed over when going through the bullet points was led by Jeff Sadler, which is a multitask modeling approach. So the idea that there'd be two target variables. So in the case of Jeff's work, it was stream discharge or river flow, but also stream water temperature at the same time, and kind of the competition between those variables, and also the information sharing that can be possible when predicting variables that have some physical relationship to one another. I would say that story, the results of that work in that paper, and it's available via archive if you want to take a look at it right now. That story is complicated, as many modeling stories are, in that multitask or multi-target approach is advantageous in some ways, but can be overly complicated in other ways. And instead of getting into the details of what those may be, I would suggest you check out that paper. But the bottom line there is, when there's lots of stream temperature data and lots of discharge data, that those two variables can be complementary to one another for predictions. But there's also additional architectures that can leverage that information as well.
All right, we have 1 more minute before the break, and we have 2 more questions. So I will take the most popular question, and hopefully, Jordan, maybe you can answer the other one in a slide or later on. So the most popular question is, what is the difference between working in federal agencies such as USGS or in university as new graduated young scientist?
Great. There are real differences between working for federal science agency and working in academia. I would say the cliche difference is intellectual freedom. So in a federal science agency, we are bound by the priorities that are funded. We have a set of programmatic priorities that we need to stay aligned with, and those constrain us a bit more than academic PIs. That's just the nature of the differences between those two. But I would argue that we do still retain a lot of freedom to explore approaches and different science objectives within those priorities. Not as much as academics, but still a good bit of opportunity to explore. There's also another key difference, I would say, that's related to stability or longevity. Our workforce model is built on a much longer rate of retention on average than the academic model, because we don't have students coming in and leaving after, say, 2 to 3 to 5 years. Our employees stay for longer. That has positive impacts and negative impacts. Positive impacts is we're able to build and invest in employees through time, the negative impact is we have a slower rate of refresh and kind of new ideas and new people coming in, because those new employees start at a lower rate than academic graduate students. And by that, I mean, we're only able to hire so many individuals per year because we have a longer retention and only so many slots open.
Great, thank you so much, Jordan. And thank you again, Libby and Jordan, for being flexible and moving up in time slots.